We're going to be talking today, it's the first of a four-part series on porosity, and we're going to be talking today about an introduction to the causes of porosity. But before we get going on that, let me introduce myself. My name is Steve Midson. I'm the president of the Midson Group, which is a Denver-based consulting company, and I specialize in castings and materials and metallurgy and things like that. I have a PhD in metallurgy from the University of Sheffield in the United Kingdom, and somewhere around 30 years or so casting and metallurgical experience. I served as a chief operating officer of 2 commercial casting companies, director of development and prototyping for a different company, and then at the beginning of my career I worked in the R&D lab for 2 Fortune 500 companies. I'm also an adjunct professor, a part-time professor at the Colorado School of Mines here in Colorado. I teach the undergraduate foundry metallurgy class. I'm pretty active in NADCA. I'm chair of the NADCA Dye Materials Committee, and I'm a member of the NADCA R&D Committee, and I've authored, I don't know, somewhere around 50 papers or so, mostly on casting and metallurgy and things like that. So let's talk a little bit about porosity. As I say, this is going to be an introduction of part 1 of 4, and really what we're going to be talking about today is what we know about porosity in die castings and basically the causes of porosity. And the idea is to understand really where porosity comes from. Obviously, if we don't understand where porosity comes from, we can't control it. And we also want to kind of discuss and explain why porosity tends to be a characteristic of our product, a characteristic of the die casting process. So the outline in terms of what we're going to talk about today, a little bit of background in terms of why we care about porosity. Then we'll talk about the major categories of porosity. Basically 2 major ones, solidification, shrinkage, and gas porosity. And then gas porosity can be subdivided into hydrogen, entrained air from this air that's pre-existing in the cavity, and then there's other things too, lubes and water, and we'll talk a little bit about that. And then strategies to reduce porosity. If we want a strategy to reduce porosity, we have to understand where it comes from, and therefore these strategies have got to be based on the physics of the formation of porosity. So that's kind of, we're trying to give some background today in terms of how this porosity forms and why it forms where it does and things like that. So again, a little bit more background about die casting. Obviously, high-pressure die casting tends to be a very common process, in fact, probably the favored process for the production of aluminum, zinc, and magnesium castings. An interesting statistic is that about 2/3 of all aluminum castings are produced by the die casting process. So if we look at all the castings that are produced in North America, 2/3 of those castings are produced by die casting. The other 1/3 are produced by all the other casting processes together. So sand casting, permanent mold casting, investment casting, lost foam casting, all together only make up 1/3, while die casting alone makes up the other 2/3. So obviously, again, it's a very popular process. Why is it popular? Obviously, we've shown here, short cycle times, gives you high productivity, tends to be low cost. In fact, quite often, a lot of castings are converted from slower processes, such as sand casting. Very good high-quality surfaces, cosmetic surfaces, used a lot with the die casting processes. Thin walls. There aren't too many casting processes that can make the thin walls that we can in die casting, such as computer cases, cell phone cases, with this new high fluidity zinc alloy. It's getting down to 0.4 millimeters or so in thickness. And so obviously in transportation and electronics, thin walls becomes very important. And then the goal is obviously to make net shape or near net shape. We want to try and minimize expensive finishing operations. We are, the ideal is if we can just cast, trim, maybe a minor amount of finishing and then ship, then that would be the ideal. And so basically what that says is that all the value of the die casting process is in the casting operation alone. And so if we get porosity, if we get defects, that is directly cost to the bottom line of the operation. Basically, we lose control the value that we put into the casting process. So it's worth saying, though, of course, that not all porosity results in scrap. Porosity is a characteristic of our process. Pretty much all die castings contain porosity. In most cases, we live with that porosity. But really what we want to do is we need to be able to control the size and the location of that porosity so it doesn't result in a scrap casting, so we maintain the value that we put into it in the die casting operation. So, why do we talk about porosity so much at NAGCA? Obviously, porosity is very common in all die castings, and here down the right-hand side of this slide, we've got some data that NAGCA collected. They did a survey of end users, people who use die castings, and asked them what was their biggest problem that they encounter with die castings. And so 35% said porosity was the biggest problem. And then another 32% said that other types of defects are the biggest problem. And many of these other defects are originating from the same underlying causes that cause the porosity. So basically, 35% and 32%, basically 67% or 2/3 of all concerns with die casting have got some relation to porosity. However, porosity is obviously a feature of our process we talked about, so maybe we need a better way to consider porosity. Consider it maybe not as a defect, but just as a feature, a characteristic of the die casting process. So our goal is not to say maybe that porosity is not a problem, but that we should say that porosity, that porosity is something that we probably ought to expect in our casting process, in our product. Obviously, from day one, we can talk to the designer, talk to the end user of the casting, and we can say, we're going to expect to get porosity, but we need to control that porosity, and therefore anything we can do in the part design in terms of optimizing that is going to be a benefit to us. And we'll talk a little bit about that later on in this presentation today. But, if we call porosity a defect, then that suggests somehow that the die cast is messed up, and that's really not, that's not true. So, we get porosity, porosity is a feature of our process. But it's only really considered a defect when it exceeds requirements, whether we get it in the wrong location, whether it's in the wrong size, or in some way it causes the part to not perform as required or expected. So only then really is it considered a defect. So we really want to kind of get some knowledge here in terms of understanding how and why porosity forms, and that allows us to therefore control the porosity better. So in this webinar today, this first webinar of 4, we're going to talk a little bit about the mechanism of porosity formation, and basically to get a better feeling for why porosity is a characteristic of our die casting process. We'll talk a little bit about alloy and alloy properties and how that can affect the distribution and the size of the porosity that we'll get in our final product. We'll talk about process characteristics and casting parameters, such as the slow shot velocity, the fast shot velocity, temperature distribution of the die can also have a big effect. And then the casting design, as we talked about, working with the part designer, their part is basically going to give us a fingerprint of where the porosity is going to form. And again, as I just said, we'll talk a little bit about some examples of that and what we can do in terms of part design to minimize the formation of porosity during the die casting process. So in terms of what are the source of the porosity, we obviously need to understand the mechanisms for the formation of porosity. If we take a kind of a typical die casting, and here we've got a schematic of or a model of a die casting, and if we cut it up in different sections, what we're going to see is we're going to see lots of pores. We're going to see these small, in this case spherical pores throughout the casting. So in this case, what's causing it? Is it gas or is it shrinkage? And then what we're going to talk about in the next few slides is in terms of mechanisms to look at the understanding based on the shape of the porosity when it forms and how it forms. So again, a little bit of background. Basically, as I said before, we have two sources of porosity, basically solidification shrinkage and gas in terms of different sources. And typically people have said that if we get smooth round pores, such as the one shown here on the left, that's probably a gas pore. If we get jagged pores, such as the one shown on the right, that's probably a shrinkage pore. In some ways that makes sense, but in reality it's actually a little bit more complicated than that. So let's talk about the two types of porosity, shrinkage and gas, in a little bit more detail. So basically with shrinkage we're talking about a volumetric contraction of the metal as it solidifies. And so basically what we're saying is that the solid aluminum, for example, solid aluminum takes up less space than does liquid aluminum. And so as we go from liquid to solid, we're reducing the size of the casting, and so we get this volumetric shrinkage. Now, unfortunately, it doesn't form on the surface; it forms in the center. As we make a casting, the heat is extracted through the surface of the casting, and therefore the first part of the casting to solidify is the surface. And so we've set the surface very early in the solidification process, and that can't change. And so if we have this volumetric shrinkage, then it can't occur on the surface. It's going to occur on the internal parts of the casting, and so we're going to get some kind of holes internally in the casting. So if we get this volumetric shrinkage, if the shrinkage occurs to the end of solidification, we're going to have grains in the casting. The grains are going to have a jagged shape. They're going to be dendritic. And so if we don't have enough material to fill the remaining holes at the end of solidification, we're going to expect to see these jagged surfaces of the grains. So that's kind of what we're seeing here again on the right. So if we think about gas porosity, if we leave out a glass of water, for instance, or if we have a carbonated beverage of some kind, the bubbles that are forming in that water, they're going to be spherical in shape. And so in that case, it makes sense to call the spherical holes gas pores. And so that's kind of where this has kind of traditionally come from. The problem is it's not totally accurate. And so in reality, what happens is the smooth pores, the ones we're showing on the left here, the smooth pores tend to be formed at high liquid fractions. They tend to form early in the solidification process when there's still a lot of liquid around. While the jagged pores, the ones shown here on the right, they tend to form late in the solidification process when there's less liquid around. So let's go back to our example of the gas bubbles in the water. Why are they spherical? Well, what happens is we've got gas surrounded by water, and what happens is the pore wants to reduce its surface energy. There's an energy of the surface, and so taking a spherical shape allows the bubble to minimize that surface energy. And the water doesn't provide any resistance. It's a liquid, so it doesn't provide any resistance to that, and so it allows the bubble to take on this spherical shape. But if you put something in the water, for instance, rocks in a fish tank is a good example. If you put the rocks in the fish tank and the bubbles are forming within the rocks, then what happens is the bubbles are no longer spherical. In fact, the bubbles will take the form of the space between the rocks. And so the bubbles that are forming in the rocks in the bottom of a fish tank, they tend to be more jagged in shape. And so, again, we have the jagged grains in the casting. So basically, it doesn't matter where the pore comes from. The pore has got to conform to the shape of the grains or whatever it's forming. So basically, again, smooth pores tend to be formed at high liquid fractions early in the solidification process when there's lots of liquid around. The liquid allows the pore to minimize the surface area and form a spherical shape. Jagged pores, on the other hand, jagged pores tend to be formed at lower liquid fractions, and therefore they have to conform to the shape between the grains, and therefore they tend to have the jagged shape as we're showing here. Now, most aluminum alloys, the volumetric shrinkage is about 6%. So what we're saying is that a solid takes up about 6% less space than the liquid, so we get this volumetric shrinkage. And so, but if you go out and look at the technical literature on die casting, basically people who've actually measured the amount of porosity in die casting, generally it's nowhere near 6%. It's less than 3%. And so what we what we're really saying is that we're actually doing quite a good job. We're doing quite a good job of feeding at least 50% of the shrinkage porosity in the castings. So that's kind of a good way to look at it. So the question really we ought to be asking ourselves is not why are we getting so much shrinkage? Maybe a better question we should be asking ourselves is why are we doing such a good job of feeding at least 50% of the shrinkage porosity, at least half of the shrinkage porosity. So we can kind of reinforce this idea a little bit in terms of the fact that the shape of the pore depends upon when in the solidification process a pore is forming. This is some information. This is from a paper by Chen and Engler from 1994, actually from the American Foundry Society Transactions. And what's it talking about is the shape of porosity that will form from hydrogen precipitating out in aluminum alloys. And we're looking at different types, different stages in the process, in the solidification process. Here we're early on where there's just a few grains. Here the grains have grown. Now we're late on in the solidification process, and here we're right at the end of the solidification process. And we're talking about the different shape of the grains that will form, and basically it depends upon the hydrogen concentration. Here, if the pores form very early, the hydrogen concentration in the alloy has to be very high. If it forms right at the end, the hydrogen concentration was very low. And so at the beginning, very early on in the process, the pores tend to be spherical. They're forming here. There's only a few grains. So there's basically nothing to constrain the shape. And so they minimize the surface energy and form this spherical shape. A little bit later on in the process, the grains are starting to grow. So now the pores are starting to conform a little bit to the shape of the grains. Later on in the process now, we're getting pretty late in the solidification process, and the pores now have to conform exactly to the shape between the grains. And now we get this very jagged shape of pores that form. And then finally, right at the end of the casting process, basically the pores are forming at the last part to solidify here at the triple point between the grains. And so we get this kind of very characteristic shape showing the triple point of the grains. And so, you know, what we're showing here is that just from one source, just from hydrogen porosity alone, we can get totally different shape of porosity dependent upon when it forms in the solidification process. If it forms early, we'll get spheres. If it forms later, we'll get these jagged types of shapes. So let's talk a little bit about porosity forming in castings, and we'll talk about shrinkage first. So here we have a schematic of a casting. Here's the casting. We've got the gate and the runner, obviously the biscuit down here at the bottom. We've got solid forming on the surface. We've got liquid in the middle, and then we've got this mushy zone in the middle. And mushy is basically partially solid, partially liquid. And obviously what's going to happen is as this casting continues to solidify, the mushy zone will tend to move towards the middle as we solidify more of the casting. So if we kind of look at a blown-up view of the mushy zone, so what we've got is we've got the surface, the solid surface here. We've got liquid in the middle of the casting, and then we've got this mushy zone where basically the dendrites are growing out into the casting, into the liquid. And so the shrinkage is obviously going to form inside the mush. It's going to form at the last part to solidify. It's basically going to form here at the base of the mushy zone. So this is the solid. This is going to be the last part to solidify as the solid interface moves off to the right. So if we're going to feed this shrinkage, if we're going to feed liquid into there to get rid of the shrinkage, the liquid has got to move all the way past these dendrites. And so basically as the width of the mushy zone increases, so the width of this area increases, it becomes more and more difficult to push liquid all the way past all these dendrites to the base down here where we need to feed the solidification shrinkage. And this is kind of shown here in this graph at the bottom where we're looking at pressure versus distance. And so if we apply high pressure here in the liquid, the pressure is going to drop off because we've got to feed the liquid all the way down this tortuous path down through the grains or through the dendrites. And so basically until we get down the end here, the end of the mushy zone, the pressure drops all the way down to zero, and therefore obviously at that stage we can't push pressure anymore, we can't push liquid anymore, and that's how we end up with the shrinkage porosity in the at the base of the mushy zone. So that's shrinkage porosity. If we talk a little bit now about gas porosity, so for instance, if we have a gas bubble that's forming in the liquid, what will happen is that we have a pressure inside the pressure of gas inside the bubble, and then we've got the pressure of the liquid metal actually pushing down on the bubble. So if we consider the two, if the gas pressure inside the bubble is greater than the pressure of the liquid, then obviously the pore is going to grow. Alternatively, we think about the other way around. If the pressure of the liquid is greater than the pressure of the gas, then the pore is going to shrink. And so we kind of know from our practical experience that this actually works. This is obviously why we use intensification in the die casting process. The goal obviously is to increase the pressure of the liquid to shrink down the size of the pores. So again, let's talk a little bit more detail about shrink porosity. Here's an example of a shrink pore. Again, we've got the jagged shape we were talking about earlier. This is actually not from a die casting. This is actually taken from a sand casting that generally we don't do quite as badly as this in the die casting process. But it kind of gives you the idea of the jagged shape we were just talking about. So one of the things I want to emphasize here is that shrinkage porosity has a much bigger impact in the die casting process than we traditionally thought. Normally, when we're thinking about porosity, we think about gas, we're talking about entrapped gases and things like that. But I think we really need to kind of take a look at shrinkage porosity to better understand how it forms. And as we talked about before, it's due to this volumetric contraction on solidification. I keep saying this, that the solid takes up less space than the liquid. And so, as we talked about before, this volumetric shrinkage in aluminum is about 6.5% or so. And so that suggests we should get 6% pores in our casting. But as I talked about before, we know we can do much better than that. Certainly, if you get a casting with 6% porosity in it, you're not doing a very good job. We know, for instance, that intensification, we just talked a little bit about this, intensification is going to force additional liquid into the cavity and help reduce shrinkage porosity. As we increase the intensification pressure, generally we'll see a decrease in the amount of shrinkage porosity. But also there's other things we can do. Changing the alloy. We talked about this right at the beginning. Change of the alloy can also reduce the amount of shrinkage. And so if we talk about aluminum, for instance, this graph here on the right-hand side is talking about the amount of shrinkage based on the silicon concentration for aluminum silicon alloys. And obviously most die casting alloys are based on the aluminum silicon system. If we look to start with at 0% silicon here, i.e. pure aluminum, this is showing the 6.5% volumetric shrinkage we've been talking about. But as we add silicon, as we increase the silicon concentration, and we follow this curve down, we see that the volumetric shrinkage decreases. And so when we get close to the eutectic composition, which is about 12.6% silicon, we can see that the volumetric shrinkage is down below 4%, and in fact, probably around 3.8% or so for the eutectic aluminum silicon composition. Same happens with zinc. If we look at this data here on the left, we can see that zinc, there's a couple of data points here, but the volumetric shrinkage for pure zinc, 5-6% or so. If we add just 4% aluminum to the zinc, now we're down at less than 3%. And so most of the Zamac alloys are based on the zinc 4% aluminum system. So we can see, again, with these alloys, we can reduce the volumetric shrinkage. So this kind of begs the question, why don't we just always cast eutectic composition? If we go back to the aluminum silicon system here, we can see that by adding 12% silicon, we significantly reduce the volumetric shrinkage. So why don't we just cast all our die castings on that composition? Well, again, unfortunately, things are not quite that simple. So let's kind of delve into shrinkage a little bit more. The problem we've got is that not all alloys feed that well. And so some alloys feed well, some alloys don't. And feeding basically depends upon the width of the mushy zone. So again, we've got this schematic casting shown here on the right, where we've got the solid, the liquid, and then the width of the mushy zone. And basically, the wider the mushy zone, the wider, my cursor to work here, the wider the mushy zone, the more difficult it is to feed the shrinkage. And so, and that kind of goes back to the graph, the figure I showed earlier. We've got to feed the liquid all the way past all those dendrites. So the longer that zone, obviously it becomes more difficult to feed through that material. And so we can estimate the width of the mushy zone. We can estimate the width of the mushy zone here based on the phase diagram, from the freezing range on the phase diagram. And so the freezing range is basically given the difference between the liquidus temperature and the solidus temperature for a given alloy. The liquidus temperature is during cooling, where we start to form the first solid, and the solidus temperature is when the alloy is 100% solid during cooling. And so the diagram at the bottom right here shows that kind of information for the 380 alloy. We're actually showing density change here, but it gives the same information, density versus temperature. And so during cooling, we obviously start on the right here, where it's fully liquid. As we decrease in temperature during cooling, we'll get an increase in density, which corresponds to the volumetric contraction we've been talking about. So it starts here at the liquidus temperature, which is about 580 degrees centigrade or so, and then it ends here at the solidus temperature, which is about 575 degrees centigrade. I'm sorry, 475 degrees centigrade. So the liquidus is at 580, the solidus is at 475. So it gives us a freezing range of about 105 degrees centigrade or so. And traditionally, these kind of alloys, when you've got a freezing range of more than 100 degrees centigrade or so, those are traditionally called long freezing range alloys. And in these types of alloys, you tend to get finely dispersed porosity rather than one big pore in the middle of the casting. And the reason you tend to get this finely dispersed porosity is that basically the whole alloy tends to be mushed during the casting process. We've got this extremely wide freezing range, and therefore you when you inject the liquid into the mold, basically the mush is forming all over the place. And so the porosity that forms in these types of wide freezing range alloys tends to be dispersed throughout the mush, throughout the casting. And so you get lots of small pores. In contrast with eutectic alloys, when we're at the eutectic composition, something like alloys 413 or 383 is kind of approaching that, these tend to have a much narrow freezing range. The distance between the liquidus and the solidus temperature is much narrower, and so in this case you tend to get large localized porosity. So the mushy zone in these alloys, the freezing range is very narrow, therefore the mushy zone is very narrow, so it's much easier to feed the liquid between the grains, and the distance is much shorter, so it's easier to feed the liquid. So all the porosity in these types of alloys tends to form in the last part of the casting to solidify. And so we'll kind of talk a little bit about here. So let's talk a little bit about short freezing range alloys. So again, we've got the schematic casting where we've got the solid, the mushy zone, and the liquid out here on the right. So let's assume, just imagine that the mushy zone is only a few microns or so. So it's microns wide, very narrow. It becomes difficult to trap bubbles in there, very easy to feed liquid down here, to feed shrinkage. So we tend to gather all the shrinkage and all the gas bubbles at the end of solidification. So they tend to be pushed all the way here to the center of the casting, and you tend to get one or a few large macro pores. So you get macro porosity in these short freezing range alloys, and so we get this kind of very jagged, very big pores in the center of the casting. Conversely, if we look at long freezing range alloys, so a long distance between the liquidus and the solidus temperature, 380, Az91D for magnesium. As I said before, the entire casting tends to be mush. And so we form grains throughout the casting, form solid throughout the casting, and therefore we tend to trap the porosity wherever it forms. And so in this case, we get micro porosity, and it's kind of shown here in this picture here, in this microstructure here, where we get lots of small microporosity distributed throughout the casting. We can also look at the effective cooling rate on the formation of shrinkage porosity, and this comes down to permeability, or how easy it is to push the liquid through the solidified grains. And so, as we know from metallurgy, the cooling rate has a few effects on the casting. It will form a casting that has smaller grains. It will make a casting that has smaller dendrite arm spacing. And so the smaller dendrite arm spacing tends to reduce the size of the feeding channel, and tends to make feeding more difficult. And we've shown here on these two diagrams on the bottom left here, both are about the same solid fraction, but what we're showing is the effective cooling rate. So we are representing the solid that forms as these gray discs, or the gray spheres. And so on the left, we've got a low cooling rate. So we've got coarse grains formed here, and then the liquid is just the white area. On the right, we've got the same solid fraction, but we've got a higher cooling rate. Higher cooling rate gives you smaller grains, gives you smaller dendrite arms, and so we've got the same volume of gray cylinders, of gray spheres, but they are much smaller in size. And so in this case, it is much more difficult to feed the liquid through this. The permeability is greater, so we've got to try and push the liquid all the way through these small grains. For instance, if we were walking through this, it'd be very easy to walk through this, through the big grains. In this case, it's much more difficult. You've got to sidestep, you've got to push your way through. It becomes much more difficult to push your way through here. It's the same for the liquid. And so it becomes much more difficult to feed here. So this is kind of a bit of a comparison between sand casting, shown here on the left, where the cooling rate is slow and you get coarse grains, and die casting on the right, where we get very rapid solidification and therefore fine grains. And so again, it becomes more difficult to feed the liquid when we've got a fine structure such as die casting. We can also look at this from simulation. So we're kind of simulating this part shown here on the top left. And again, it kind of helps us understand why porosity is a characteristic of our process. So we've got two types of simulation. The one on the left here is looking at the liquid fraction, and then the one on the right, we're looking at the velocity, the speed at which the liquid is flowing into the die. And in both cases, we've got early on in the process where we're starting to form porosity, and then later in the solidification process where the gate is fully solidified. So let's first look at porosity initiation. We're starting to form. We can see the solid fraction is getting quite large here at the gate. So we're starting to get some mush forming, but we've still got very large pockets of liquid left in the casting. And so these are going to form shrinkage. And so this is a good indication of why shrinkage is a characteristic of our process. If we continue the simulation to be a little bit later, now, as I said before, the gate has fully solidified. We can see that over here from the velocity. We no longer have any velocity through the gate, and therefore we've got no longer any ability to feed additional liquid into the casting. But we still have significant pockets of liquid here in the casting. We've got a pocket here, maybe a little bit here. So basically, we know the volumetric shrinkage is 6%. So basically, 6% of this remaining liquid is now going to be porosity, whether we like it or not. So that's kind of another point on this. That's why it's important to talk with the designer. We talked about here, if we can avoid some of these heavy sections and make the casting more uniform thickness, that would help us in terms of trying to minimize the amount of shrinkage that will form. So in summary, for shrinkage porosity, we can say that shrinkage can account for all of the porosity that we see, although that's not necessarily that's where it's coming from. We're going to talk about gas porosity in the next few slides or so. So we're not saying that all porosity comes from shrinkage, but clearly we need to give shrinkage equal weight in our porosity considerations. And in terms of reducing shrinkage porosity, feeding, anything you can do to feed more liquid into the mold, in terms of bigger gates, higher pressures, more uniform wall thickness in the casting, and then alloy design, as well as we just talked about. So now let's talk a little bit about gas porosity. So there's basically three major causes of gas porosity in castings. Hydrogen gas, and often hydrogen will give you pinhole porosity, such as shown here on the bottom left. Then entrained air, that's air that's pre-existing in the cavity that gets trapped into the casting. And then thirdly, we've got evaporation of lube. If you've got too much lube on your die, or you've got water remaining in the casting, when the liquid metal comes in, it's going to heat them up, it's going to vaporize them, and it's going to cause entrapped lubes or entrapped water vapor in the casting. It's very difficult, and this is part of the problem that we've been talking about, it's very difficult to separate the gas porosity easily from the shrinkage, because often what happens is the gas will actually fill the shrinkage pores. And so that's one of the reasons why it's a bit difficult to tell them apart. So now let's talk a little bit about hydrogen porosity. Hydrogen porosity comes from hydrogen that's actually dissolved. This is for aluminum die casting alloys. Hydrogen it becomes actually dissolved in the liquid aluminum. So with this graph here on the right, the vertical axis is the amount of hydrogen that's dissolved. Often it's given in units of cc per 100 grams of aluminum, which is kind of a strange unit, while on the right here is just kind of weight percent hydrogen, something we're more used to. And then we're looking at temperature. And so here is about the melting temperature of aluminum. So on the right here, we're showing how much hydrogen becomes dissolved in liquid aluminum. On the left here, we're showing the maximum amount of hydrogen that becomes dissolved in solid aluminum. And clearly, we can dissolve much less hydrogen in the solid aluminum than we can in the liquid aluminum. And so what happens is that as you're melting the aluminum reacts with water that's in the air and from other sources too, and it will actually the oxygen from the water will react with the aluminum, produce aluminum oxide, you get free hydrogen that dissolves in the aluminum. And so during the solidification, the hydrogen gas becomes rejected because it can't be dissolved in the solid, and you get porosity forming. It precipitates out as porosity. Typically, it either has micropores or will combine with a larger pore present in the casting. So that's hydrogen porosity. Now, in terms of entrained air porosity, this is probably the most commonly thought of in die casting. This is air that's caught during the filling, either in the shot sleeve during injection or due to pore venting. And so the bottom diagram shows here. This shows a kind of bad wave formation during the filling of the shot sleeve. Probably going to entrap a lot of air here, and then that air is going to get carried through with the liquid and into the casting. And here's an example of a very big gas pore in an aluminum casting. So it tends to be difficult to predict exactly where this is going to form, and certainly in terms of the size of which it's going to form. Certainly if you've got a bad die design, maybe you've got liquid that's impinging from two different places, that's probably going to trap some air. But there are a whole number of process variables and designs that can affect the amount of air entrapment. Vacuum can be effective. Obviously, a lot of die casters use vacuum. There's kind of a saying that vacuum can help a badly designed die, but vacuum doesn't have a lot of effect on a well-designed die. But certainly, there's a relatively new process out there called high vacuum die casting, where people are making very high quality, generally automotive parts, structural safety critical parts with very, very high vacuum processes. So certainly vacuum can be effective. And then there was a process in the 80s, mostly in Asia, I think, where they actually injected pure oxygen into the cavity. The thought being that if you cut up a hole, such as the one shown here on the right, basically all you find in there is nitrogen. You don't see any oxygen. Air, of course, is about 80% nitrogen, 20% oxygen. So what's happening is the oxygen is reacting with the liquid aluminum, or even the hot solid aluminum during solidification, and so it gets the oxygen is totally tied up, and so that all you see in the pore is the remaining nitrogen. So the thought being is if you can remove all the nitrogen from the die, then you won't get any porosity. And so people tried that, was relatively successful. I think he had a couple of problems, one of which is that you're basically replacing your porosity with aluminum oxide throughout the casting, so that's not great either. And also, obviously, there's some safety issues in terms of actually filling your cavity with pure oxygen. So that was a process that was really not that successful. Then other types of porosity, dilube, plunger lube, water, hydraulic oil. If you've got too much dilube on your dye, then the excess is going to vaporize during the filling process, and it's going to produce hydrocarbons, and so that's going to cause problems with gas porosity. Plunger tip lube, the same. If you use an excessive plunger tip lube, that can vaporize during the filling process and end up as porosity in your casting. Water. If you apply too much water to your dye, then maybe you cool the dye down too cold. The water can't all vaporize before the next shot. You've got some liquid water remaining somewhere in your dye, trapped behind a slide maybe, or something like that. You inject the liquid aluminum into the mold, heats it up, vaporizes. You're going to get entrapped water vapor in your casting. And the same with hydraulic oil. If you've got leaks of hydraulic oil or leaks of heating oil, again, that's going to vaporize and cause porosity in the castings. And so certainly the color of the porosity can help. If you cut up the casting, if you've got pores such as the one shown here, and you cut them up and look at them under a microscope, if they're dark, then generally that's from lubricant, because you've got burnt carbon or something like that in there. If they're light or shiny, then it's water or air. We can talk a little bit about the effect that intensification will actually have on the size of the pores. Intensification can't eliminate air porosity. Once you trap the air or the water or the lube or whatever it is in there, it's going to stay trapped in the casting. But you can reduce the size of it, and you can reduce it quite considerably. And so we can kind of go through a calculation here. This is talking about the ideal gas law. Ideal gas law is PV equals nRT. P is pressure, V is volume, N is a constant, R is a gas constant, and T is temperature. But we can kind of change the configuration of that equation a little bit and look at using Boyle's law. We can say that V, the final size of a pore, the final volume of the pore, is going to be the initial pressure divided by the final pressure divided by the initial size of the pore. So let's kind of run through a quick calculation, and hopefully that'll be a bit clearer. So if we've got, for instance, an 8 cubic inch casting, we have no venting, so basically all the air is going to be trapped. So basically we've got about 10 cubic inches of air that gets trapped. If we just assume that we get 100 spherical pores dispersed in the casting, at atmospheric pressure, those pores are going to be about 0.56 inches diameter, so about half an inch diameter. However, if we apply intensification pressure, so now this is the final pressure in the Boyle's law equation shown here. So the initial pressure is atmospheric, the final pressure is 10,000 psi, and we look at the effect it has on the volume. It shrinks the pores down considerably. So from 0.56 at atmospheric pressure to 60 thousandths of an inch at 10,000 psi. So this is the effect that intensification is having. We know this from die casting, but what it's saying is we can't eliminate the gas pores once they're in there, but we can shrink them down to a much smaller size. And then obviously the intensification is only going to last until the ingate freezes. In that case, then the pressure is quickly going to drop down to a vacuum. Kind of go through the Boyle's law calculation again. This shows that the final pressure goes to 0. This implies infinite volume for the gas pores. Obviously, that's not obviously going to happen. But what essentially does happen is the gas then fills all the shrinkage voids with gas, and so the shrinkage voids and the gas voids now become connected. And so again, this is part of the reason why it's a bit difficult at times to tell them apart. So porosity reduction concepts. We've kind of talked a little bit about this in terms of solidification control, in terms of the alloy. With short freezing range, we can reduce microporosity because we get more feeding, but the downside is going to be that you're going to get one or big macro pores. And so it depends really on the type of the casting, whether you want to get one big pore or whether it would be better to have a lot of small pores. So with long freezing range alloys, we're going to reduce the macro porosity, but the downside is we're going to get a lot of dispersed fine porosity. Directional solidification can certainly help. This is something that's used a lot in squeeze casting, but certainly can help in die casting. Here we're kind of showing a shot sleeve here with the casting going downhill, and then in this case we've got a very hot plunger, and that's going to keep the gate open longer and allow us to push more metal into the casting. Bigger feed pass we talked about. Obviously, that'll remain mushy or semi-solid longer, allow you to feed more liquid in there, and uniform wall thickness. In terms of eliminating remote thick sections, we talked about that in the part design. In flow control, obviously filling the shot sleeve, shot parameters, gating and runner, venting design, vacuum, dilute. All these things obviously can have an effect, and these are some of the things we'll be talking about in some of the future seminars. And then let me just talk quickly about gas control. Obviously, you can do degassing of hydrogen, although the amount of hydrogen tends to be small in terms of the overall gas content of the casting. Certainly minimizing the amount of the shot tip lube, minimizing the spray is going to help you. So those can certainly have an effect too. So in the next seminar, we're going to be talking about the process parameters and the effect on porosity and the magnitude of the effect. And kind of shown here is a kind of a summary of the parametric studies looking at the effect on porosity. The ones at the top have a large effect on porosity. The ones on the bottom have a small effect on porosity. So intensification pressure we talked about, spraying we talked about in terms of the permeability. And then as we kind of get down towards the bottom, the in-gate or the initial metal temperature, the dwell time, and the capillary pressure have smaller effect on the overall porosity. And we'll talk about this a lot more in the next seminar, in the next webinar.